Hello, I'm John Chivacco, the co-chair of the NY-GEO 2023 conference and a board member of the New York Geothermal Energy Organization. I'd like to welcome you to this recording of a live presentation from the conference, a two-day event which was held in Albany, New York on April 26th and 27th of 2023. This year's educational sessions and keynotes represent the latest in ground source heat pump system design, product innovations, and installation practices, along with important policy, regulatory, financing, and incentive updates. This presentation is one of over 40 sessions from the two-day event, all of which were recorded and available at NY-GEO's website, www.ny-geo.org, along with session descriptions and a link to download the slides from each of the sessions presented. NY-GEO is proud to make this content available to our members and other industry stakeholders, and if you are a member, thanks so much for your support and participation. If you find this content valuable and for some odd reason you are not yet a member, consider joining NY-GEO at the appropriate membership level with details available at our website. The live recording from the NY-GEO 2023 conference will start in just a moment. Thanks so much for listening.
So here we go. This is going to be a little bit like 2 + 2 at the beginning, but by the time you get done here today, you're going to be able to understand the context. By the way, by a show of hands, this is about what I expected for the second day of Geothermal 101. There's probably about 20, 25 people in here. By a show of hands, how many feel like they know a little bit about geothermal heat pumps to begin with? Raise your hands. Okay, so everybody here knows a little bit about geothermal heat pumps. So I'm glad everybody has a little bit of exposure, and I hope that this is going to give you what you need to understand the context and verbiage of heat pumps. We're involved in the code development process for the International Association of Plumbing and Mechanical Officials. We work with the trades very closely. The terminology you're going to hear today is standardized internationally. You're going to understand the importance, adaptability, and benefits of the technology as not just, and you heard it today, it's not just a good idea, it's vital, absolutely vital to the infrastructure and building. We're going to understand why the technology is also important to health and human safety. It should be obvious, but we're going to talk about it a little bit. We're going to understand the barriers to geothermal adoption. The barriers are coming down right now. Thank you for turning that down a little bit. The barriers are coming down a little bit right now, as we talked about this morning, because we have the trifecta. Dan Ellis mentioned during our morning plenary, I love that he said this, you need high energy costs, you need incentives, and you need construction all at the same time, and we have that right now. We are going to talk to help to understand and internalize our collective capability and responsibility to make these changes, and then I want everybody to feel comfortable with leaving with the intent to study, specify, and apply heat pump technology and for safe buildings in every application going forward. Now, here's where the rubber hits the road. We're going to talk a little bit about the difference between air source and geothermal heat pumps. As you can see, an air source heat pump always has an air component outside to exchange heat with the outside air. So a geothermal heat pump always has some type of component that connects it with a heat source or a heat sink. Usually that's known as the earth. Now the earth doesn't have to be the only one, and that's part of what we're going to talk about a little bit later in the session. So notate that geothermal can also be infrastructure tie-ins of any type, and we're going to talk about some exciting things with that as we go through Geothermal 101. Think about a geothermal heat pump as your refrigerator. Now, a refrigerator uses the Carnot refrigeration cycle. That means it has a compressor, a condenser, an expansion valve, and an evaporator. Those are the four components in any Carnot refrigeration system. Now, if your refrigerator had one more component, it would be truly a reversible heat pump, and that would be a reversing valve, right? So a typical air conditioner, which most people understand, whether it's a window or a split system like this, is designed to pump heat out of a building to the outdoors. A refrigerator, interestingly enough, is designed to do much the same thing. It pumps heat out of the box and onto the floor. That's usually where the condenser of the refrigerator is, and you can feel that manifest in that nice warm temperature when you go to get that midnight snack from your refrigerator in your bare feet. It's pumping heat out of the box and onto the floor. Now, next time you go by the refrigerator, notate, that's warmth hitting your feet. Where is that heat coming from? How is that happening? That is the magic of the Carnot refrigeration cycle. I'm not going to teach the principles completely here because it's it's more of a 4-hour class to do the Carnot refrigeration cycle. So either you understand it or you don't. Otherwise, it's a little bit like your iPhone. It's just something we know that works, right? What the Carnot refrigeration cycle does fundamentally is it takes a volume or a specific amount of gas, compresses it without adding any heat. It compresses it, and what that does is that same volume of gas, once compressed, is manifest in that same energy into a much smaller space, and it drives the temperature up so that the heat from the box, which is 40 degrees, can be dumped onto the floor by your feet at more than 100 degrees. And that's what it does. It basically manipulates heat and moves it uphill so you can drop heat off. Now, if you want to heat this house, what do? You put in the reversing valve, and instead of pumping heat out through the condenser, and we've all put our hands over an outside condenser and felt the heat rejection. In the reverse mode, if you've ever felt a heat pump outside in the heating mode, it's ice cold air. And as a matter of fact, if you've really paid attention to it, these freeze over because moisture condenses on the coils, it freezes, and there's a defrost cycle. So that's one of the inherent challenges of absorbing heat from the outside. Once you get below freezing, it becomes harder and harder to extract heat from the outside air. Not impossible, just harder. Now, the geothermal system, unlike the air source system, is not suffering or challenged with outdoor air temperatures. So in the middle of the winter time, when it's below freezing outside, the geothermal heat pump is extracting heat from a medium that is well above freezing, actually 55 degrees year-round, and that is the ground. And that's why a geothermal heat pump has more efficiency, because its heat source is warmer in the wintertime, and its heat sink, when it's 80, 90, 100, is cooler in the summertime. So whatever part of the year, you're going to have an unfair advantage when you compare it to an air source heat pump. If you go on, if you've paid for admission here today, which of course you have, and you go on the NY-GEO site, after you will find downloads of this presentation as well as many others, and I won't have time today, but I want you to, if you really want to understand the heat pump cycle, just click on that YouTube link, and it will show you if you're really interested in heat transfer and fluid flow and phase change. There are generally 3 different ways to distribute energy in a building. You can distribute it through forced air ductwork. You can distribute it through a radiant in-floor system, or into actual radiators in the walls. In addition to that, a geothermal system has the option, a very inexpensive option, of a domestic hot water generator. That's why these 2 lines are going down to this domestic hot water tank. What they normally do is they passively create hot water at a really usable temperature between 130 and 145 degrees if you choose, while the system's running anyway in the heating or cooling mode. So when we say passive, that means it's just dumping heat into the hot water tank. The hot water tank in these situations usually has some type of backup strips, and we won't have time to talk a lot more about that today. Just understand that geothermal, unlike air source, also has basically a standard option. Almost everybody uses it, and that's a domestic hot water generator. Now we're going to talk about how heat pumps are rated, and this is probably the most important part of this class, to be able to understand energy efficiency ratings. And I see this young lady from Halco in the back. She's nodding because I know she's been through all of this, and thank you for being here. I really want to thank a lot. There's so many good people. Halco is a very big mechanical contractor in upstate and western New York. So just really appreciate all the representation of many good companies here. So this is review for a lot of us, and this is really kind of an interesting take, because there's two ways heat pumps are rated. There's actually three, HSPF, but I'm not going to talk about that. I'm going to keep it down to the basic two: energy efficiency rating and coefficient of performance. Energy efficiency rating is the net cooling capacity in BTUs delivered by the applied energy in watts. Now, having been to high school math, basic math, I can tell you the first thing they always said to us is don't mix units. When you do mix units, you end up with a funky result that is not really representative of anything. And though it will give you an energy efficiency rating that you can compare to others, the rest of the world, the United States, is the only country that regularly uses EER. COP is used for both heating and cooling internationally. And COP is the simpler equation because it's the BTUs delivered divided by the BTUs consumed. Or you can do it another way: kilowatts delivered divided by kilowatts consumed. You can do it any time, and it's beautiful when it's the same units because you have something that really makes sense. And before we get into doing some of these calculations, let's consider something real quick. The basis of heat transfer in the world is typically the British thermal unit. A British thermal unit is equal to the amount of heat that one wooden matchstick creates as it burns from top to bottom. That 1 BTU, how much heat is that really? I know it'll burn my hand, but if you apply that heat completely to be absorbed by 16 ounces of water, it will raise that bottle of water 1 degree Fahrenheit. Now that we know what a BTU will do to 1 pound of water, what will a watt of electricity do to 1 pound of water? Well, it's important to understand that 1 watt of electricity equals 3.4 BTUs. Now, so if you apply 1 watt of electricity in heat to 1 pound of water, how much do you think the temperature of that water will go up? Anybody want to guess? 3.4, exactly, we're following. So 1 watt of electricity, if you apply it to a bottle of water, is going to get the temperature up 3.4 degrees. Now, this is where the correlation comes in. EER equals COP times 3.412, which means this is where they mixed it up here, net cooling capacity in BTUs divided by the applied energy in watts. There's not going to be a test. I'm just telling you the funkiness of the rating system. Now, here's where the rubber hits the road. And I want everybody to everybody knows a space heater. This is no different than a blow dryer or an electric resistant stovetop. If you give it 1 kilowatt of electricity, it's going to deliver 3,412 BTUs of heat. That is a given. That is simple. That's what we call electric resistance heating. You're burning raw electricity through hot wires. You're putting it through, they glow red, and they create that heat. And it's usually driven by a fan or something to get the heat off of the coils. Now, that same kilowatt of electricity going to one of these heat pumps right here is going to not burn electricity to create heat. It's rather going to drive motors. There's a few motors in a heat pump when you think about it. There's the fan motor out here. There's a compressor in here, or in this refrigerator. There's a fan in here. So you've got all these different motors, but it's just driving electrical components that are moving. Their only purpose is to move energy from one place to another. So if it was an air source heat pump like here, you would be moving energy from the outside air through a heat pump and into the space. In this case, this is an example of a geothermal heat pump that's pulling it with 1 unit of electricity from the grid. It's able to extract 4 units of heat from the earth for a grand total of 5 units of heat delivered in the space. That unit there, this example, is a 5.0 COP, meaning 1 unit of electricity delivers 5 units of heat. It's a very simple division. But here's the amazing thing. This is why $250 billion has just been appropriated for geothermal systems, as you just heard earlier, plus all of the other benefits, because we can get 17,060 BTUs, just a single standalone snapshot for every kilowatt of electricity into a house. Now, here's the trick. This isn't just for heating. That same heat pump can take that 5 units of heat energy out of the house and put it back into the ground. That's air conditioning. And that's the funny thing we have to understand. In this room here, it's got a duct system. This duct system can deliver heat into this room or pull heat out. And if it was a heat pump operating, that heat would be pumped out of here in the summertime to the air outside. In the wintertime, it's pumped out of the air and into here. In a geothermal application, it just does it more efficiently because the ground is a constant temperature. Now, what you're going to hear about later is you can do this in another way, where you take waste heat from one building and put it into another building, and the COP in that case, and 5.0 COP is good, a very good COP for a heat pump. I mean, it's obviously, it's not even comparable here. This is, and I'm jumping around a little bit, but this is what's going to save our electric grid as we decarbonize and electrify. We can't handle 1 kilowatt only creating 3,412 BTUs of heat. That will break our grid, just like we saw in Texas a couple of winters ago when they had that cold snap. That was because almost everything was electric, and they had a lot of electric resistance heating and heat pumps, and the cold snap just taxed the grid too much. There were a few other contributing factors. That's what New York, very wisely, because they have a very well-funded program administrator called NYSERDA, who is a major sponsor here. They recognized that 10 years ago when we first got involved with them and said, air source heat pumps are good, but we can't do this without employing geothermal too. And that's because of this and some other things we're going to share. Now, yes, you have a hand? Yes, oh, absolutely. It is part of the solution. And so when, and part of this is an educational process, Carrie, where air source heat pumps are going to go in like crazy. What the government nationally and locally here in New York is trying to do is fix the infrastructure so that people can hook up to these geothermal heat pumps without having to get a drill rig on each property. Right now, that's the only way people know is, and we're going to talk about that, but I appreciate you bringing that up. Air source is definitely a big part of the mix. We're just talking about the geothermal. Yeah. So this is really cool because you can kind of get a view here of a geothermal heat pump and an air source heat pump. These are both Carrier products. I just wanted to do that. Every major manufacturer has an extended range water source heat pump line. Every one that I know of for sure. And so you can find these. This is not unusual. This is, as we said, a very robust and mature technology. So this could just as easily be a geothermal as an air source. It's a matter of, is there something for the heat pump to tie into? for a geothermal heat pump? Well, the only way you can have something to tie into for a geothermal heat pump is if you drill a borehole or tie into some type of ground-coupled infrastructure. And that is why with a geothermal heat pump, there's nothing outside, because whatever we tie to is typically underground. An air source heat pump is exactly like a geothermal heat pump fundamentally, because it's got all the same components. It's just put all into one case. There is a compressor in here in the bottom. The blower section is upstairs. And so to give you an example, these are all different types of geothermal heat pumps. This is a PTAC, just like you would see in any apartment or hotel room. They come with geothermal components in them. Or you can also get most of these types of units air source. This would be a residential grade unit. This would be like for a 4 or 5 star hotel unit. These are called stackable geothermal heat pumps or water source heat pumps. These are PTACs. This would be a horizontal water source or geothermal heat pump that would be, for example, above a ceiling here between floors in a building. This would be a vertical mechanical room heat pump, another mechanical room heat pump. A few other types include dedicated swimming pool heat pumps, dedicated domestic hot water heat pumps, and they're usually identified as water to air, water to water, horizontal, vertical, modular, stackable, and they have all these designations. When you're a contractor or a designer and somebody has their hand up, and I'll get right to you, you say, I need a vertical water to air, and they know what you want. Now, I have a question in the back or a comment. Yes, I will. I know exactly where you're going on that. When you're in the cooling mode, and this unit here or here is cooling, you have a tremendous amount of waste heat you're pumping into the ground, because you're taking heat out of the building and you're pumping it into the ground. So in that case, that heat pump takes that heat, and before it puts it into the ground, it dumps all that heat into the domestic hot water tank. So the COP is actually, I don't know, I've never actually run it, because you're improving the COP of the unit by actually dumping the heat in the domestic hot water tank before you put it in the ground. Do you have something further to add on that, on your thoughts on that? Obviously you know a little bit about it. Yeah. Okay. There is a separate coil, an NSF rated coil inside of there, and right off of the compressor, which is indicated right here, there's a super hot gas line, and we install, and it's not shown here, we install a desuperheater coil, and that hot gas is usually coming off out at about 160 degrees. And so what the desuperheater does when it's pumping heat into the domestic hot water tank is it's improving the efficiency of the system by grabbing that superheat and dumping it in through an NSF water to refrigerant coil into the tank. I'm glad you asked, because I didn't know if you were going beyond that, but the COP is well above 10 for a desuperheater. It's so astronomically high, it improves the efficiency of everything in the system. That means you're simply in a refrigeration cycle, you have a certain amount of heat needed or compression needed to turn the refrigerant from a gas into a liquid. So anything above that threshold from a gas to a liquid, that's called phase change, is called superheat. So you're taking the superheat off of the gas that is kind of overheating or overcompressing of the gas anyway, and you're making the system more efficient. So you're basically, it's taking waste heat off of the refrigeration cycle. So it's better than good. It's like helping the system. So I appreciate the questions, really good questions, and you're making sure I'm staying on my toes too, because one of the most advanced questions I've ever had in 101, actually. All right, so in addition to what you just saw here, we have rooftop package units like you would have on a Walmart or a Best Buy. We have 100% fresh air units. And this is something, and I get to go for 24 more minutes, but if I were to finish anywhere in 101, I would want to finish here with everybody basically understanding that there are a lot of benefits to geothermal technologies that people don't normally think of. And so put on your thinking cap and try to remember this, because when you can conversationally mention one or more of these 7 points beyond just energy efficiency and decarbonization, you're adding to the benefits of geothermal in a way that people really appreciate. So first of all, we've talked about this a little bit already. No more outdoor equipment to replace with a geothermal system. Why? Because everything's underground typically. They are more hurricane and storm resilient because there's no there's no equipment outside. So storms and hurricanes can't affect them unless they take out the building too, typically. The system longevity goes up by a factor of about 3, and that's according to the DOE. You go up from 10 to 12 years outdoor equipment lifespan to 27 or more years for a geothermal heat pump. And why? Because that little heat pump isn't outside, it's inside, usually in a mechanical room or a garage or something like that. So like a classic car, which would rust and crumble if it sat outside in the curb, if you keep it in the garage, it's going to last a lot longer. And that's exactly, these heat pumps outside of a building, they don't fail. The reason they fail typically at 12 to 15 years is just weatherization. It's just a lot of outdoor, taking abuse from the outdoors. We obviously solve the combustion and decarbonization and electrification issues with geothermal heat pumps. Here's something that people don't realize until they actually get it. We have a much more comfortable cooling and heating environment because the heat sink in the heat source is more normalized, meaning it's about 55 degrees year round. So we have better and more comfortable cooling and heating. We have remarkable system efficiency at standard equipment pricing, meaning these heat pumps, they don't cost any more than an air source heat pump has the same components in it as a geothermal heat pump. So it's going to an equal genre, meaning if you buy a builder grade heat pump, you can buy a geothermal or an air source for about the same price. If you want the bells and whistles, you just pay a little more, but you can get either one for about the same price because there's nothing special about a geothermal heat pump in most cases, except that it ties in with the earth. Thermal energy network wells and piping are permanent infrastructure. Just like a water line or any well you put in the ground, infrastructure is, when I say permanent, it's going to last 60 years or more. It depends on the quality of the construction. So a little bit about the history of these heat pumps in a city-based system. Around 2010, West Union, Iowa, Merlin Dunt said, as long as we're tearing up the streets and sidewalks to put in new water mains, we might as well improve the energy infrastructure at the same time. And from that came a downtown thermal energy loop that serves all of the downtown buildings. And we're going to talk a little bit more about that in just a few minutes. The interesting thing here, and the reason I bring this up is, this is like, we've had several efforts to get our community, meaning the national community, electrified. It started in the 50s with the National Electric Manufacturers Association. They were doing a major push for all electric homes. They basically, and if you were to read this, it talks about how all electric homes are safer. Think about what we're going through right now. We were doing that in the 50s. It's 2023 now. Now, you might ask, and this is part of 101, this is a little bit of history. You might ask, why does it keep going forward and backward? There's something that few people know about that happened just before this. During World War II, at the beginning of World War II, the U.S. was shipping oil from Texas up to New York with tankers. But guess what happened within the first month of the beginning of our insertion into World War II? 70 of our tankers were sunk off of the East Coast in 1 month. And what do you think the U.S. did about that? They said, we got to pipe it. We got to pipe it from Texas to New York. So they did an emergency construction project and ran 2 pipelines from Texas to New York. It took 355 days, just short of 1 year to do that. Now, go to the end of the war, the pipelines were purchased by the companies that were, the oil companies that were contracted to install it, and they took what they learned, and guess what they did during the 50s and 60s? They installed 2.5 million miles more of pipe in the urban infrastructure of our cities, which is what is our natural gas system now. So at the same time, while NEMA is trying to, and we didn't have natural gas piped at this time. So at the same time as they're starting to roll out this all-electric idea, the gas industry says, oh my gosh, we can get this bridge fuel, natural gas, to everybody. So they got a lot of subsidies. So at the same time as this is going on, we're running, and now it's 65 million people in the U.S. are hooked up to the natural gas system. So it's important to understand how we maybe could have done this in the 50s and 60s, but we are doing it now where we are piping the U.S. It's the point of me telling this story is what we did in the 50s and 60s in the U.S. is what is happening now. It's just the difference is before it was natural gas pipelines, now it's going to be geothermal energy network pipelines. And that's what Donovan Gordon was talking about this morning that are going into, that they're funding these projects, these 56 projects going into the New York market. Now that we're at 15 minutes, I keep looking at my watch because I don't want to keep anybody over. This is an example from Atlanta, Georgia, of a comparison between, and this is a very fair comparison. Many comparisons are starkly more, they make geothermal heat pumps look even much better than this. But this is a great example of the first floor being air source heat pumps, and the second floor, and this is a brand new install in 2010, being geothermal heat pumps. And ASHRAE, since they're the guiding, one of the guiding engineering associations for HVAC, they monitored the heck out of it and corrected for BTUs and kilowatts per square foot. This is what we got. The geothermal heat pumps peak out here in June, July, and August in energy demand and consumption. The air source heat pumps peak out here. Now the air source heat pumps, because they're exposed to sub-freezing temperatures outdoors, peak out in the wintertime. It's a matter of simple thermodynamics. If it's cold outside, it takes more energy to extract heat. Nobody's picking on anybody. It's not unfair. I mean, it's not an unfair analysis. It's just a fact we need to know. And so if you wonder why the electric grid would suffer with an electrification, this is it right here. We have an electric grid that can support our summertime air conditioning load, right? This is what everybody's screaming about. If we go to an all-electric building stock, where are we going to get this extra electricity from? And now with a geothermal system, and this bears out anywhere in North America, whatever your cooling load is, if you have a cooling load, a lot of places don't, but the point of the matter is, whatever your cooling load is in the summertime, your heating load in the wintertime will be lower with a heat pump. It's a no-brainer because there's always heat underground. Always heat underground. at whatever this design temperature is. So the sub-freezing temperatures outside in Atlanta, outside in New York, do not affect the heat pumps in the winter time the way the geothermal heat pumps, the way they do the air source heat pumps. Another example, in Oklahoma, a Climate Master did a study on 2 brand new office buildings built side by side and this is the corrected for BTUs per square foot, the energy consumption of the geothermal throughout the year, and the wintertime peaks are in the middle on this graph, as opposed to on the edges on this graph. And look at just what we're talking about here. It levelizes the grid, kind of what you see here. It's a little more pronounced here. In Oklahoma, it was a lot more flat. But look at that peak. This is what we're talking about. Now, I want you just to get your heads around this fact. If we totally, like we're doing in the US right now, if we subsidize geothermal rollout, for every dollar that we as an American taxpayer pays into the system for geothermal incentives and geothermal subsidies, we will save $3 for electrical upgrades. In other words, we have to get this electricity somewhere, so if it costs $1 trillion to do a geothermal rollout nationwide, we'll save $3 trillion in energy infrastructure. There are great reports on that. We don't have enough time to go through those now. But why else, you might ask yourself, why else would the U.S. government, New York government, and every other forward-thinking government throughout the world and the United States be spending money on geothermal infrastructure now? And the answer is because it will really reduce our electrical infrastructure upgrades over the next 30 years. So this is a very strategic approach that you're getting an idea of here in Geothermal 101. Dr. Xiaobing Liu, who stood up last at the plenary, he created this document as a scientist at Oak Ridge National Laboratories, and it's not just a good idea. This is based on 7,000 U.S. government residences that they're built for officers and you can read the report. You literally just Google assessment of national benefits from retrofitting existing single-family homes with ground source heat pumps. I love the government. It's always, you read the title, you know exactly what's in it. But look at this. 56 at 100% penetration, 56% reduction in summer and winter peak electrical demand, and 45.3% reduction in carbon emissions. I'll just leave it at that. Here's a report that Ontario did in 2020 that simply says, I'm going to decipher this for you very quickly. If they get everybody off natural gas in a snapshot, because everybody's on natural gas that can get it, and certainly the rural communities, they aren't. But here is what they estimate they will have to spend to subsidize an air source heat pump rollout. $435 billion. There's about 6 or 7 million people in Ontario. If they subsidize a geothermal heat pump rebate program, it's $137 billion more. The electricity savings over the time period will give them the payback and wash out even with the subsidies. But here's the really important part. This is the reason this report is important. They will reduce power infrastructure expenses by $500 billion. And if you think about it, Ontario's smaller than the population of New York City. So you can see why New York City, and our company is one of the companies that is fortunate enough to be working on these thermal energy networks in New York City. This is what they will save in a community of 6 to 7 million people. So if you extrapolate that or expand that out in New York State, I haven't done it, but there would be trillions of dollars of savings, is what you'd figure based on this in electrical infrastructure by doing this investment first. Not only that, but uninhibited rollout of air source heat pumps in urban settings is not pretty. It looks handsome at first, right? Everybody loves to see an air source heat pump, a beautiful installation of an air source heat pump sitting beside a house or hanging outside. But this is the reality of it, folks. People get creative. I don't know about you. I was a contractor that actually climbed climbed plenty of extension ladders myself, did a lot of unsafe things, changing compressors and units. I would not want to be on this extension ladder replacing one of these units. I would not want to be there. And I can tell you, I bet you when they started doing this, the first couple of these line sets was nice and square. And then after that, it just kind of became, you can't see it from my street. It's okay. And it really begins to look third world. And this is what we're running into is, and this is why the unions and the federal government and the state government are so determined to keep the unions involved. Because not only does it keep the quality of the work up, but it makes this type of a thing not possible, it takes it out of the mix of difficulty, because the geothermal units, and here, there's another one, are all, I'm jumping ahead now, are all inside. And I'm going to show an actual an installation of loops here as we start to roll back. I'm sorry I have to roll through some of these a little faster. I kind of have some things I want to focus on. So this is what a geothermal installation typically looks like in a single family home. And this is why it's all underground and out of sight when it's done. This yard here is this yard after it's done. This is actually done for, we wrote an article for National Geographic about 15 years ago. The senior sustainability officer for the U.S. Navy, and this is right outside D.C., did this in his house and went off the grid. It was just a great, and this is actually on the DOE website. You could see the actual operation. It was a net zero house. And the only way they were able to go net zero, interestingly, on this, they had to get the demand down by putting in a geothermal heat pump. Otherwise, they wouldn't have even done that. They had to get it down to where it was manageable because they didn't have enough rooftop space for solar. They wanted to do a single net zero installation. So now that we've covered a couple of those things, in the last 10 minutes, I want to talk a little bit about variations in loop systems. I promised I would do this. Hybridization, energy share, heat exchange, and thermal energy networks. There are about 7 major different geothermal exchange systems, and there are about 25 variations from there, which give you almost an infinite number of hybrid opportunities. We have city center, urban center projects going on around the world, and none of them are the same. Everyone has different components because there are so many different ways to share energy. You can use, this is a water-based water source geothermal heat pump system. This is a DX, direct exchange, where they actually use refrigerant in the ground. So you can see it has a very small footprint on a DX system versus a water system here. It's got great applications in many places, and a company that makes these is represented here at the conference. They love bragging about these because they can use a very small drill rig, put in a DX spider coil, and get great heat transfer. Another type of technology is called a downhole closed loop dynamic closed loop exchanger, and it forces advective water flow through a downhole exchanger. This is all super advanced stuff, but it's just giving you a taste of all the different types of systems you can use. This is an aquifer thermal energy transfer system, uses 2 well points, and is excellent for high volume applications in commercial projects, such as the dynamic closed loop system. And just to give you an idea of another hybrid system, this is one of the coolest things. Now, there's no other system exactly like this of which we are aware. This is the Cornell Ithaca campus. They use Lake Cayuga as the heat sink for their cooling. Now, imagine this, Lake Cayuga is about 40 degrees down here at the base. At 40 degrees, how much mechanical cooling do you need to cool a building? 0. That's the temperature that you send through a coil to do all of your air conditioning. So they literally cool their whole campus, what we call passively, through exchange with Lake Cayuga. They do have the chillers there to back up if they have a problem or anything like that. But look at that. They have no mechanical refrigeration needed because they're using a resource that's available. Now, is that available everywhere? No, not everybody has surface water available, but that's why it's important to consider it. If you think this is only for northern climates, we're working on a project right now in South Miami. There's an aquifer at 3,000 feet in depth that has 40-degree water. It's like drilling for energy. Do you know how much that's worth to the downtown Miami area? Well, we're doing a study on it, and it's going to be worth billions over the next 30 years of energy they don't have to spend. But do you know what? Miami has that, but Orlando doesn't. It's just one of those things where you have to study each site because sometimes you have hot resources. You see this? Earth heats. Cornell just drilled a 10,000-foot hole that has more than 200 degrees Fahrenheit. Right now, they get the heat for this campus from their CHP plant. What is a CHP plant? Blah, blah, a combined heat and power plant. A combined heat and power means they make their own electricity. They have for decades made their own electricity right here. They're islanded. And the waste heat from generating electricity is used as a part of the heating solution for the campus. But guess what? CHP is not the answer for the, is not going to be the answer for a permanent solution. So this well they drilled, they want to use it not only to replace the heat they're getting from the CHP plant, but they slowly want to idle the CHP plant down, and they're hoping to get some electricity out of this. That's called enhanced geothermal. We don't know. They just drilled the well. Either way, they'll get the added renewables coming onto the grid to tie in and be able to idle this down. The best use of natural gas out there right now is to create electricity. You get a higher coefficient of performance from natural gas by creating electricity than anything else. If you just burn natural gas, it's at best 95, 97% efficient. If you use it through an electricity generator, you can get well over almost 2 COP in certain applications, especially if you're using this heat. So it's a great way to use this bridge fuel, and this is a perfect example of a learning laboratory. So I took you from the basics of understanding COP to understanding an actual learning laboratory. There's another Cornell campus on Roosevelt Island that has another great geothermal system that operates completely different from this. And this was installed in 2013. Christy and I gave a tour of this to several co-op boards and engineering firms just last month. It's an amazing campus that operates very effectively. So in these I'm going to jump to something else. This is what I want you to think about. In any thermal energy network, which is basically taking a geothermal, we're at 11 o'clock, so I need to wind up, taking a geothermal system and making it an energy utility, and that was what Donovan Gordon was talking about today. You can use any number of sources and sinks. In this case, they're using aquifer thermal energy transfer, closed loop boreholes, surface water exchange, you can see it here, and they're using wastewater. Last thing I'm going to be able to say, because I got to give up the podium after this, is wastewater energy transfer has the potential, without drilling a single borehole, to handle 40% of the heating and cooling needs for an average building. So there are about 8 modules, 4 hours each, that explain all this, that were created and put on the IAPMO, International Association of Plumbing and Mechanical Officials website. If anybody wants more about it, just Google NY-GEO. We will direct you to that site when you ask us, or stop Christy or I afterwards. We'll give you a call and send you information on some of that stuff. And that's it for today. Thank you for coming to Geothermal 101. Appreciate it, everybody.